Yeah. Hello everyone. Namaste. I am Ramnath who would like to share with you some information on the VLSI topic, STA setup and hold and its physical significance. Please feel free to provide your comments and any suggestions. Thank you. Yeah. Before going to the main topic, I want to briefly mention that so many systems in daily life are triggered at specific events. For example, a rising sun triggers flowering of plants and many events that happen in our daily life. Flights and trains are scheduled at regular intervals so that largely the overall system works predictably and reliably. In the same way, a digital system having many digital components with lots of interconnection between them can operate with specific uh, triggers which are of regular in nature. So a digital system can be modeled as a finite state machine where a regular triggering, which is a feature of synchronous behavior, can be realized, and that will have so many digital propagation between registers to register at the stroke of a clock signal like this. So here the digital system can be mapped into a finite state machine, and where the signal will be moving from one register to another register at the strike of a clock signal. Yeah, we have seen earlier that synchronous logic is implemented using register to register logic, which is realized through D flip-flop. As you know, the D flip-flop contains master and slave latches. The D flip-flop, which is having the master and slave latches, will be having the transmission gates and back-to-back connected inverters. So if you see, and before we go further on how it is implemented, we will briefly discuss about the transmission gate. So this transmission gate graphical symbol is in this way, and its actual implementation will have the PMOS transistor and NMOS transistor. NMOS transistor will be connected with to select signal, and opposite of that S bar will be connected to the PMOS transistor. So based on this truth table of the transmission gate, when the control signal S here it is 1, then whatever is the input that will be transmitted to the output. However, if the control signal S is 0, then the whatever, even if the output input is 0 or 1, the output resulting will be high impedance state. That means the transmission gate will purely block the input reaching the output when S equal to 0. So we will see here that how the when clock is in logic low and logic high, how the data moves from one location to another, from D to Q. Okay, so here if you see, when clock equal to low, when clock equal to 0, I mean, then clock bar equal to 1, so this transmission gate will be on here, and it will send whatever is the input signal to the output signal, because clock equal to low, so clock bar equal to 1, so it will be conducting. And in this scenario, clock equal to low, so clock equal to, it will block the movement of the input signal. So this whole thing will not 2 and the 2 data will not reach to 5. So from D it will reach 1 and then 2. It will also reach 4, but this transmission gate is blocked, so it will not go to 4. 4 data will not reach 1. So data has now moved from up to 1, from there to 2. Okay, but since this transmission gate is off, so the data will not move to Q. So when there is clock equal to low, the data has only reached up to 2. And if you see here, the whatever was earlier, the logic state of Q that is retained during this clock equal to low state. There is no influence of the logic state 2 on logic state 5. Now when we say clock goes to logic high, we will further see how the data moves. Okay, when clock equal to high, you will observe that clock bar equal to 0, so this transmission gate is off. Okay, and you will also observe that this transmission gate is on, so whatever was the data at 4, it will reach 1 and it will be retained in this state through this back-to-back connected network. So this data will be retained here. Aside to that, it will also move in forward direction and hence it will reach up to Q. Okay, however, since this transmission gate is now off, whatever was at 6, it will not reach, only it will reach only up to 8 and it will not reach 5. So effectively the data at 2 is now reached Q. So that means it needs clock 1 full cycle for the data to move from this point to all the way input state to output state of the flip-flop. So that is this point we will discuss later. So here if you observe that this whole thing is an ideal situation. That means like transmission gate is perfectly working with the zero delay, inverter is working with the zero delay. So that is why you are having a perfect operation. Okay, so this is one way of implementation. We will understand the non-ideal behavior of the flip-flop further. Here we will consider the same D flip-flop where it has the positive edge trigger clock. So here the information here what we are going to discuss will be same. So in the clock, when the clock is equal to low, the data will move all the way up to 4 node and it will not move from node 2 further. Okay, so that is true, but here we are considering that the transistors have finite delay to propagate. So the data, whatever, see now whatever is the data here, it will move up to node 2 and now this data need to be captured properly. So before now at this point when the clock transition to high, this is the positive triggering, so this transmission gate is going to be opened. So at this stage when gate is to be opened, the data at 2 has to be stable before the gate is turned on. Now it is blocked, now it is going to be on. So before that the data has to be stable here. So that is what we are mentioning, that is the setup time. Okay, so that will be the setup time. And one more thing is like when the data after the clock triggering edge has happened, it doesn't mean that you can change the D because the transmission gate is blocked. No, because now since we are considering that is the non-ideal nature of the transistors, so this transmission gate has finite delay, this transmission gate also has the finite delay. So there is a small iota of time when these two transmission gates will be on and the data at deep port can go up to all the way up to 5. So after the clock triggering has happened, you need to ensure that the data has to be stable for some more time so that the transmission gate 1 is closed fully, that means like blocked fully, and this is on fully. So this data will be correctly captured from node 2 to node 5, and after some time, after that time, what is called hold time, then the data can be changed. So that is the thing what we are talking here in terms of setup and hold. So that is how in the D flip-flop where we are talking about the positive edge triggering, setup and hold will come into play. This is the physical significance of the setup and hold in a flip-flop. That is why during the hold operation, the data will be checked at the same clock edge. Okay, in this same clock edge only we are checking whether the data is changing or not. Okay, and in the case of setup, we need one more clock cycle by when the data will be modified. Modification will be uh, detected. So that is one reason why setup checking needs one clock cycle and hold checking needs to be done at the same clock edge. If you take the analogy of a person getting into the train, then before the train arrives, the person has to be on the platform ready to be boarded. That is the setup time. And once he got into the train, he has to be stable in the train and should not get out before the train moves. So that is the hold time. Okay. So we will be able to know more about the setup and hold in the coming slides. Yeah, as discussed earlier, in the non-ideal case, it is where the data has to be stable before the positive edge of the trigger of the clock. Okay, so here we are considering the positive edge triggered flip-flop. So here the data has to be stable before the clock trigger, and the data has to be stable for some more time so that the data is properly captured. During this time, the data can be changing, and once the data has been captured properly, after this time also data can be changing. Yeah, that is about the setup and hold time. Yeah, and coming to the next one, these are the references I have taken, and thanks to these people for providing me the good videos, and also to VLSI expert for blog where I have taken the previous slide.